In this video I'll be discussing simultaneous solutions or simultaneous equations, which I like to think of as linear functions that intersect. In this particular video we're going to be looking at linear functions. When I say functions, I'm referring to linear functions. Consider the graph below illustrating the growth of two different species of trees. What I have here is a graph representing two different growth rates of two different types of trees, which I call tree A and tree B, and listed with the linear functions describing their rate of growth. On the y-axis I have my height, which is given in metres, and on the x-axis I have time, which is given in years. You will note at some point here time zero on the y-axis indicates the height of tree A and tree B when these trees were both initially measured. Okay, so this was the initial measurement. For tree B it was 3 metres tall, and tree A it was 8 metres tall, and that's also suggested by the y-intercepts of their function. So what we have illustrated above are two linear functions on the same xy axis. It is evident that at some point or some time in years the functions will intersect, which appears to be somewhere up around about here. Now the intersection of these two functions will occur when they are equal to each other. One other way that you could go about determining the intersection point is obviously just drawing in an extension on these two functions and actually locating the point at which they intersect, and then moving down to the x-axis to determine at which time they did so. You could then substitute that time value into the function, either one of these functions, to get their corresponding height. But what you might find happens most of the time is these two functions may not actually intersect until a very long way off the graph, in which case it's not realistic to just extend these lines to find that intersection point. So the way we're going to go about doing this is actually substituting and solving algebraically. What I've done is I have rewritten tree A and tree B with their corresponding linear functions and listed them as equation 1 and equation 2. If I have to refer to them in the future, that's how I'll refer to them. So how do we determine at what value on the x-axis, being the time these two functions intersect? Well, if this is our first function, y equals x plus 8, and this is our second function, y equals 4 on 3x plus 3, then x plus 8 must equal 4 on 3x plus 3. And I've called that equation 3. If that doesn't make sense, the reason being is because y equals y in both equations. That is, this is this, therefore that must also be that. If we rearrange 3 and try to solve for x, we've essentially identified the x-axis coordinate of the intersection, being the time component, which is what we're going to look, which is what we're trying to find. So rearranging 3, which is up here, I'm going to rearrange to solve for x, which will be the x-axis coordinate for the intersection point, which will tell me when these two trees are the same height. I've rewritten equation 3, and then I've moved my positive 3 to the other side and made it a negative 3. So the positive 8's become a positive 3. Subtracted 3 off it. And then need to move the x to the other side. And what you will note is x is actually equal to 3 on 3x, because 3 on 3 is just 1, so it won't change the value of the x. The reason why I'm saying 3 on 3 is because we've got a 4 on 3 here, so to make the subtraction a bit easier. So 4 on 3x, take 3 on 3x, is 1 on 3x. I can then move the 1/3 to the other side by dividing this side by 1/3, or I can actually move the 3 to the other side by multiplying. Either way, it's going to give me a result of 15, which means that the x-axis coordinate at the intersection point is 15, meaning it's 15 years at which the trees will be the same height, or 15 years have passed after the first measurement was taken. So therefore trees A and B will be the same height after 15 years. To determine the height at which the trees are equal, which is 15 years after the initial measurement, all we need to do is substitute that value 15, so x equals 15, into either of the original equations, 1 or 2, being over here, equations 1 and 2, to solve for y, which is the height. So I'm going to substitute x equals 15 into equation 1. The reason for that is because equation 1 is much simpler than equation 2. It has a fraction in it, so I just simply need to add 8 to 15, which gives me the result of 23. Y, the y-axis, remember, is our height, which is in metres. So I can put metres on the end of the 23. Therefore, after 15 years, both tree A and tree B are 23 metres tall.